Hello. I want to discuss some theorems and definitions related to sequences. The topics related to sequence and series are taught in different parts of the world in most of the graduate and undergrad course. So I'll start from the definition of convergence of a sequence. Basically, I use my definition from the book entitled Introduction to Real Analysis by Robert J. Bartle and Donald Hartsterbart. I start from the definition of convergence of a sequence. So, definition. A sequence. This is denoted by xn, and n starts from 1 and goes to higher order. A sequence xn in real number r is said to converge to a point x in R if for all epsilon greater than 0 there exists a natural number k, let's say epsilon, to indicate that k is dependent on epsilon, such that the number n is greater than k epsilon, implies the sequence xn minus the point x is less than epsilon. So if a sequence has a limit, then sequence is said to be a convergent sequence. If it has no limit, then a sequence is said to be a divergent. So if you have xn be a sequence of real numbers and x is in R, then this is equivalent in saying that for all epsilon greater than 0, there exists a natural number k such that for all n greater than or equal to k, the term xn satisfy x minus epsilon is less than or equal to x n, which is less than or equal to x plus epsilon. In other words, this means xn lies in between x minus epsilon and x plus epsilon. So it is better to write strictly less than. So this is the definition of convergence of a sequence. So for natural number k epsilon and the subscript n, greater than k epsilon gives this value. Okay. So there is a theorem. There is a theorem. And I'm not going to prove this theorem. This theorem is about a uniqueness of a limit. That means the theorem states that a sequence in R can have at most one limit. If the sequence has two limits, for example, we can say L and L prime be two limits, or we can say like this one, X or X prime be two limits, then X and X prime are equal. That means if Xn, we can say this n tends to infinity limit, Xn is equal to X, then it should be equal to X prime. Symbolically, we can write this one as n tends to infinity, a limit Xn, this is equal to X. This gives the convergence of a sequence. Okay. A sequence, bounded sequence, a sequence, let's say we can write Xn is said to be bounded if there exists a real number, if there exists a real number, you can say m, and this m is greater than 0, such that the value of a sequence in absolute sign is always less or equal to m for all n belongs to set of natural number. So this is the definition of bounded sequence. Okay. So there is a theorem related to this bounded sequence. The theorem says that a convergent sequence of real numbers is bounded. Okay, I want to prove this. let's suppose let xn converges to x, because our hypothesis is that the sequence is convergence. Then so we need to prove the sequence which is convergent should be bounded. So this is convergent, this means convergent, and we can write the limit xn approaches to x, or xn approaches to x as the n tends to infinity. Okay, let epsilon is equal to, epsilon is equal to 1, then there exists a natural number k. K depends upon epsilon, so k is the function of 1. So I simply write k. There exists a natural number k such that xn minus x is less than 1. Generally, we can write the xn minus x is less than epsilon. And here in particular, I took the value of epsilon to be 1. So this gives the condition xn minus x less than 1 whenever for all n greater than or equal to k. Here we apply triangle inequality. Thanks for triangle inequality. Now, the value of xn, this one is equal to xn minus x plus x. It will be easier if I write in this notation. From triangle inequality, we can write this one is equal to xn minus x plus absolute value of x. And given that xn minus x is less than 1, so I can write this one is 1 plus absolute value of x. So this xn is less than 1 plus absolute value of x. We can say that the sequence xn is bounded here. So we have another thing here. If we setting some m, this is equal to supremum of some element of the sequence like x1, take the absolute value of x1, x2, and up to x k minus 1, because n is greater than or equal to k, we take the subscript up to n k minus 1, and the last number is 1 plus x. So m is the supremum of all the elements taken from this x1, x2, xk minus 1, and 1 plus x. So this m is greater than every element. In other words, all the elements are less than or equal to this m. So this follows that. So we can write this xn is less than are equal to, because the element 1 plus x belongs to the elements, and the m is one of the element from x1, x2 up to 1 plus x. So if I take the value m for all n belongs to natural number, then we can say that m is a particular number. Then we can say that the sequence is bounded. The sequence is bounded. So this proves that every convergent sequence, we use the definition of convergent here. And by using this one, we prove that the sequence is, the convergent sequence is bounded. That's it. Okay. I will now prove another theorem. There are series of theorems like if xn is convergent sequence converges to x, yn is a convergent sequence which converges to y, then xn yn converges to x times y, x plus y, xn plus yn converges to xn, sorry, x plus y. But for it, if I take minus sign, then it will be hints like this one. And another c, if xn divided by yn, then it converges to x divided by y. Here, the number in the denominator not equals 0. Okay. I'm gonna prove the first theorem. Let me clear this. Okay. So proof first A, that's given xn converges to x, yn converges to y, to prove xn yn converges to xy. Okay, now I use triangle inequality here too. This xn yn minus xy, this one is equal to xn yn. I subtract the number xn y and I add this term here, xn y minus xy. This one is equal to, from here I factor out xn, then I have yn minus y plus I factor out y, and then xn minus x. So I use triangle inequality. Then I can write xn yn minus y plus y xn minus x. So this can be written as xn, because if you have the absolute value of two real numbers, then it can be converted into separate absolute value, separate numbers with absolute sign. So yn minus y plus is y and xn minus x. Okay, so let me write this one as equation 1. This is inequality 1. And then, okay, from previous theorem that a convergent sequence is bounded. We just proved that a convergent sequence is bounded. So we can write, since a convergent sequence is bounded, so there exists a real number m, we take it positive, such that if I take the sequence xn, then xn is less than m. So let's take it m1, doesn't matter. For all n belongs to a natural number n, suppose we set this m by supremum of two elements. This one is, first is m1 and second is y. I said this one because I need to use this condition in inequality 1. So I want to erase the above. Okay. Then, so what's the value here? Then xn yn minus x times y, this one is less than, we have from 1 xn yn minus y plus y xn minus x. Since xn and yn converges to a point x and y respectively, so we can conclude that since xn converges to x and yn converges to y, so for all epsilon positive, there exists a natural number k1 and k2 such that n greater than k1 implies xn minus x less than epsilon divided by 2m, because I can take the number epsilon divided by 2m. Similarly, and if n is greater than k2, then yn minus y is less than epsilon divided by 2m. I'll clear this one. So there are k1 and k2. Let k is equal to supremum of k1 and k2, then if n is greater than k, this k is dependent on epsilon here. I want to erase this one. So if n is greater than k epsilon, then we conclude that then from here xn yn minus xy is less than or equal to this xn is bounded, so I can write m, and for yn minus y I can write this one epsilon divided by 2m. So I simply write I want to jump now, just I simply copy this one yn minus y and then plus, so y is also bounded, so y is less than or equal to m, and I simply copy the last term xn minus x, xn minus x. So now this one yn minus y is less than epsilon divided by 2m, and xn minus x is less than epsilon divided by 2m. So I can write this one as m times epsilon divided by twice m plus m times epsilon divided by twice m. So this twice m is here, twice m is here, cancels out. So this is equal to epsilon divided by 2 plus epsilon divided by 2 gives epsilon. Since epsilon, a positive quantity, is arbitrary, so it proves that the sequence xn yn converges to x comma x times y. This concludes the proof of the theorem. Similarly, we can show the rest of the proof in this way. Thank you.